Collins, I think, should be given a lot of credit in the sense that to eliminate the IF transformer, they developed a mechanical filter. Now, so when we're talking about the piezoelectric effect, it's a similar effect. If you can couple together mechanical discs of certain diameters, you can then produce a resonant effect to produce this IF curve under a very controlled condition, make it narrower, and also produce it pretty flat top. There were other filters. There were crystal filters that produce the same thing in present-day receivers. There are other materials besides quartz that exhibit this piezoelectric effect. The material called barium titanate is an example. I don't want to get off the subject, but barium titanate has the same effect. It will develop its own voltage as you strike it with an electrical impulse. And the depth sounders, by the way, are used. The barium titanate transponders are used in depth sounders. I've never seen any of them, but there are types of filters that are non-crystal that use this barium titanate effect, even at RF. But the trouble with most of them is that they want to work at low audio frequencies. Mechanical filters now work similar to a long tube musical instrument, let's say a clarinet or a reed instrument that produces an impulse, and as you put down keys, you lengthen or shorten the length of a tube. And so in essence, the mechanical filter is a series of discs connected together in such a way that one disc will have a slightly different frequency than the other, so that the combination then will produce this IF frequency curve, but they do not work piezoelectric. It's a mechanical, it's an acoustic filter, let's put it that way.
So Collins was one of the major innovators then in receiver design.
I would say they were the major innovator. A lot of these things had to do with the development of the crystal itself. They started out with crystals and they determined at certain axes that you cut the quartz across a certain axis. Well, they started out with, let's say, an x-axis. They found out that was fine. That would create, the crystal would oscillate. But there were also, as they went on, they found out that by changing the axis, the temperature coefficient of expansion of the crystal was different. So that by cutting these crystals, of course, the basic quartz crystal, we're talking about that great big hexagonal thing that you dig out of the ground, they subject that to X-rays in order to determine what the proper angle of cut is, and then they cut it with a diamond saw. See? So they found out that by slightly changing the angles, they could get crystals that would, all crystals drifted a little bit. That's the point I wanted to make. The first crystals were not right there. They moved along as they warmed up. Their thickness changed, and so their frequency changed. But they found out that by determining there were certain cuts where the coefficient of expansion was such that crystal probably moved this way as it moved this way. One way canceled the other.
What were some of your most memorable ham receivers from a performance standpoint?
Well, you mean those that I built or those that I bought?
Either.
Well, I think the first Collins receiver probably was outstanding. To begin with, it didn't drift. It had so many other factors. The tuning was good.
75A1?
75A1, yeah. I had one and I liked it very much. And I had built a number of other receivers. As a matter of fact, even to the point in the early days of building the superhead on a great big aluminum box about so-and-so, and we actually had a compartment in there for a storage battery, believe it or not, and a back compartments for 3 or 4 so-called B batteries. I think they were 22.5 or 45 volt batteries. They were a big cell like that, and there were 3 of these fitted, and the whole thing was completely sealed. That was the idea, so that it wouldn't pick up any noise from power line. And see, we haven't even discussed rectifiers and receivers, because this was another really outstanding thing. See, that to be able to operate the receiver other than batteries. See, so because you had the filament, you had to light the filament, so you had to have what they called an A battery, which by and large were dry cells, which you never see anymore. Then the high voltage, they were 22.5 and 45 volt rectangular containers of batteries, and these batteries used up juice, and so they wore out, and they're expensive, and so that your A battery, which lighted the filaments, and your B battery, the early receivers, when this first screen good tube came out, all this was battery operated. It wasn't until probably in the 30s sometime that rectifiers were brought out. When the rectifiers were brought out, it was necessary to make transformers. It was necessary to come out with electrolytic capacitors. And don't you see that as the need arose, then technology developed it. The electrolytic capacitor. See, the early capacitors were all wax paper and tin foil. And to get 25 or 30 microfarads, it took a tremendous, great big device. So when the electrolytic came along, you could get 50 microfarads, and the filtering action of these things eliminated a lot of choke coils and that sort of thing, which were necessary for filtering. And so as the rectifiers came in, first of all, they were gaseous rectifiers, and then mercury vapor came in for their other higher voltage. Every time you ask a question, you bring up another phase that came in. See, the transformer field was, while the transformers were well known and they made them for spark and all that sort of thing, inexpensive transformers that would develop 150 volts or 100 volts and all were transformers themselves. The type of core material, the windings, the coupling of the windings, the gaps in the transformers, all these things were outgrowth of transformer development. See, again, because there was a need for high voltage power supplies that didn't work on batteries, then you had the need of the thing. Well, don't you think this pretty well covers it?
No, it's just
well, I mean, we haven't even gone into the. I could sit here all night and talk about the development from where we're going to stop here.
Well, so. I wanted to hit the high points of development, and I didn't realize that it was this interactive and
oh yeah, everything. See, and we haven't even started to talk about the interaction like our present day receivers. See, that's an entirely different ballgame. With the introduction of solid state, now we come up with frequency multipliers. Don't you see? We could start out with a low frequency oscillator. By the way, controlled by again a solid state device with good stability, because the masses were small and they weren't nearly as subject to expansion changes with atmospheric, so that you could come out with a pretty good oscillator and multiply it 100 times, 1,000 times, 10,000 times, see? So that finally then the idea of oscillator stability was virtually completely eliminated, jumping way ahead, by the phase-locked loop. See, and here it is. In other words, as it moves, it brings itself back. And so that it sits in there and the stability is always right in there.
One of the first receivers that I ever had that used a phase-locked loop was the National HRO 500. And it had a little light on it. And whenever that light was on, your loop was locked. Mm-hmm. And the loop was locked in increments of 500 kilohertz. Mm-hmm. And then later on, it was 100 kilohertz. And then it was 10 kilohertz. Mm-hmm. And now, like on the Eddystone, it's one cycle increments.
Yeah.
But that evolution of how phase-locked loops, they started off very broad, and now they're...
Well, you see, all of these things were created by need. Some guy didn't just sit down and say, well, I got an idea, I'm going to develop a phase-locked loop. He developed a phase-locked loop because he was trying to get stability. And now he had solid-state techniques to work with, which he didn't have before. See, going back again, we're talking about just getting off the path of receivers. Frequency measuring devices. See, we didn't have solid state, so what we had to develop in this thing were the frequency measuring devices were multivibrators, and so your first counters came up as a result of these multivibrators, which were originally kind of a wild thing that sometimes they worked and sometimes they didn't, and then they'd get working together and oscillate. But see, the multivibrator played a tremendous part, and the vacuum tube, of course, played a tremendous part in the changing that over into solid state type of thing. See? So everything, each one of these things interlocks.